All right, welcome ladies and gentlemen. This is my lecture for Friday, March 6th. Obviously I'm not here today, so today you're going to be learning about the three heat equations that are listed on table T in your reference table. You're going to practice using them a little bit, learn about all the components of them, what each variable means, and then know when to use which one. So that's really the goal. You'll see that you've got a homework assignment that goes along with it. Basically our goal is to be able to correctly answer these problems. So first up, there's going to be a few definitions, and so we should have our notes out, our notes on thermochemistry out, and open to where it says delta H and enthalpy. And we're going to need our calculators today, and we're going to need our reference tables today. So that's what we need: notes, reference table, and calculator. Delta H, which is enthalpy, is often referred to as the heat of reaction. And essentially, really all you need to know about delta H, it's basically just a chemistry word for heat. It stands for enthalpy because, you know, when I look at the word enthalpy, clearly it starts with an H, so let's call it, you know, H. Makes total sense. Totally see where they got that from. And the delta out in front, the little triangle, we read that as delta, and it means change in. So really this is basically saying sort of the change in heat of the reaction. How much heat did the reaction lose or gain? That's what enthalpy is. We can have heat that didn't come from a chemical reaction. If you rubbed your hands together with friction, via friction, you can generate heat that way. That's not enthalpy because you didn't actually perform a chemical reaction. But if you mix two things together, like we did in the small lab on Thursday, and you see that there was a change in heat, you did see that the temperature altered, which reflected that, then we're talking about enthalpy. So heat sort of associated with a chemical reaction. That's all it is. So just see this and be thinking about heat. That's really the connection that you have to make here. Now, the first thing that I want to say about enthalpy is table I in your reference table. So have a look at table I. Table I is a listing of lots of different chemical reactions and their specific chemical reactions. You see there's all kinds. We've got some synthesis, we've got some dissociation, some decomposition, and we've got some combustion. And you'll see that delta H written on the top right-hand corner. And the title of the table I is heats of reaction. So this is basically telling you, how much heat in kilojoules, that's what that right-hand column is, how much heat was exchanged in this particular chemical reaction. But what I really want to have you notice is what I have up here in quotations. The minus sign indicates an exothermic reaction. So if we see a negative out in front for any of the values that are in table I, that's telling us that that reaction is exothermic and it releases heat. That's the amount of heat that is being lost or being given off by that reaction. If a minus sign indicates an exothermic reaction, you'll notice that little star, the little asterisk next to the delta H, and then we look on the bottom of table I, it tells you that. Minus sign indicates exothermic. Then a positive sign has to indicate endothermic. So minus is exothermic, plus sign is endothermic. This is basically this idea is basically saying that, look, if you're losing heat, then your heat is in the negative. You're getting rid of it. Whereas if you're gaining heat, your heat is in the positive. So that's why we use that negative sign for exothermic and positive sign for endothermic in chemistry. As an example, have a look at this reaction. Find it on table I. NH4NO3 goes to NH4 plus NO3 minus. See if you can find that. When you do find it, I want you to pay attention to the delta H value and its sign. So the delta H value is positive 25.69 kilojoules per mole. That means that if you have 1 mole of NH4NO3 solid and it reacts via this equation, then 25.69 kilojoules will have been exchanged. And that positive sign means that this reaction is endothermic. Right? That reaction is endothermic. So you cannot simply tell by looking at a chemical equation if it's exothermic or endothermic. You don't know. There's absolutely nothing in the chemical reaction, if it is a chemical change and not a physical change, you cannot tell simply by looking at it if it's exothermic or endothermic. So you have to look at table I, because table I will tell you that, whether it's exothermic or endothermic. Well then, using that, then, we can address this question right here. What is the enthalpy, the heat of reaction, when 1 mole of lithium bromide, LiBr, breaks down in water into aqueous lithium and bromide ions? Is this an exothermic or an endothermic reaction? So on table I, find a reaction that represents this. It's 1 mole of lithium bromide, LiBr. So we want to break that. We want to find that breaks down into aqueous lithium ions and bromide ions. So you want to find that reaction in table I. So we're scanning for something that looks like this. LiBr solid goes to Li plus Br minus aqueous. Hopefully you found it. So the enthalpy for this reaction, just reading straight off of table I, delta H minus 48.83 kilojoules per mole. That means that 48 kilojoules are exchanged in this reaction, and that negative sign out in front, as the table tells us, means that those 48 kilojoules are lost. It's an exothermic reaction. All right, specific heat. So that's a comment on enthalpy. So if we see that word, just know that it basically means heat, the heat of a chemical equation. Specific heat, which is abbreviated as capital C. Of course it is, because when I read the phrase specific heat, clearly it starts with a capital C, so let's use a capital C to represent it. Makes total sense. Don't know what you're complaining about. The definition of specific heat, it's a constant. The amount of heat required to raise 1 gram of a substance 1 degree Celsius. It's a constant for any substance. It does not change based on how much of the substance you have. It's pretty set in stone. It's something that you can look up in on your reference table. There's a section of your reference table that lists some specific heats. You can look it up in other, or basically reference materials. And on your reference table, what we're going to pay attention to is table B. Table B lists the specific heat of water. Specific heat is the amount of heat required to raise the gram of a substance 1 degree Celsius. So if you're looking up on table B, which is where we should be looking now, you want to find where it says specific heat, and the specific heat of water is 4.18. 4.18 joules per gram degree Celsius, or 4.18 joules per gram Kelvin. It doesn't matter if it's degree Celsius or Kelvin, because if you change 1 degree Celsius, you have also changed only 1 degree Kelvin, right? Because to turn Celsius into Kelvin, you've got to add 273. So like 0 Celsius is 273 Kelvin, 1 degree Celsius is 274 Kelvin. You've only gone up by 1 degree either way. So that's why the units are interchangeable for specific heat. Now what this is saying is if I have 1 gram of water and I want to heat it up by 1 degree, I need to add 4.18 joules. That's what this unit is saying. That's what specific heat is saying. How much energy does it take to heat this thing up by 1 degree, and if you just have 1 gram? And the way that we use specific heat is by measuring heat flow. If we know how much energy it takes to heat up something, a substance, a certain amount of a substance, then we can sort of predict, if we have a larger sample of this substance or a smaller sample, how much energy will be required then. And the way that we do that is by this equation, Q equals MC delta T. We're using our reference table a lot today, so I'm going to have you turn to table T, which is where we have all our formulas and equations, and find this equation on table T. Hopefully you notice it's under the section that says heat. So we've got, my AP kids sometimes call this the MCAT equation. Gosh, I wonder why. There are 4 components of this. There are 4 variables, and if you kind of look at table T, you'll sort of see that. We have Q, we have M, we have C, and we have delta T. So the triangle thing in the middle, that's a delta, and it means change in. And so it's not a variable unto itself. It's talking about the temperature. There's Q, there's M, there's C, and there's delta T. Q, as we talked about on Thursday, Q stands for heat, because, the word heat starts with a Q, so that totally makes sense. Q is heat. And the heat can be gained or it can be lost, but it's going to be in joules. When we're using Q equals MC delta T, heat has to be in joules. M is mass. Mass has to be in grams. The reason is that we basically have to match it up with C. Our next component of Q equals MC delta T. Capital C is the specific heat of a substance. For water, C is 4.18 joules per gram degree Kelvin. If you have a different substance, it will not be 4.18. It's kind of like density. It's like freezing point. It's like boiling point. Specific heat is very specific to whatever substance it is that you're working with. And then the last bit, delta T. Change in, when we put that triangle out in front that means delta, which means the change in, it's always, always, always final minus initial. Delta T is not large temperature minus small temperature. It's final temperature minus initial temperature. It's entirely possible to have a negative value for delta T if you if you end at a lower temperature than you began at. That's how you get a negative delta T. You can get a negative number, and that's totally acceptable. Because if we get a negative delta T value, that means that Q turns out to be negative if you're keeping that negative there, and that just means that heat was lost. That's how we use signs when we're talking about thermochemistry. So delta T is not just big number minus small number. You can absolutely have a negative value for delta T. If you get one, it simply means that heat is being lost by the system. Negative meaning it's exiting, it's sort of leaving the system. So if Q is negative, heat's lost, you have an exothermic reaction. If Q is positive, however, if you don't have a negative value on delta T, if delta T is positive, then we get a positive Q. That means that heat was gained by the system and you actually had an endothermic reaction. Now mass is always going to be positive and specific heat is always positive. So basically M and C are always going to be positive, but delta T can vary. So remember that delta T is just one thing. Right, there are four variables in this. There's Q, there's M, there's C, and then there's delta T. Four components. Q equals MC delta T. So we're going to look at a couple problems with this. So get your calculator out. What is the heat required to raise the temperature of 60 grams of water by 20 degrees Celsius? In this problem, we have water and we are changing its temperature. Q equals MC delta T is all about if you're changing the temperature of something. So this is the formula that we're going to use for this problem. Breaking down the problem, what information have we been given? Well, right there, 60 grams. We know the mass of the sample. We know it's 60 grams. And then by 20 degrees Celsius. So we're raising the temperature of this something by 20 degrees Celsius. That's our change in temperature, right? That's how much we want to change the temperature by. We don't know if we're raising it from 20 to 40 degrees Celsius or from 40 to 60, but we do know that we want to raise the temperature by 20 degrees Celsius. Continuing to read this problem, what is the heat? Meaning that's what we're looking for. The part of Q equals MC delta T that is heat is Q. Remember, Q and temperature are not the same thing. They are related, and they are related through this formula right here, but Q is not the same thing as temperature. Q is heat, and heat is about transfer, energy being transferred from one thing to another, versus temperature, which is all about the motion of the particles. Heat is not about the motion of the particles. Heat is saying what energy is being transferred from the system or into the system. So heat is not T, right? Temperature is T, heat is Q. They're two separate things. And so we know we're looking for Q, which means that if we want to use Q equals MC delta T here, we have to be able to know what C is. Otherwise, there's no way that we can solve the problem. And that's when we have to know how to use our reference table. The substance that is being asked about here is water. On table B, they give you several constants for water, one of which is specific heat. You do not need to memorize that the specific heat of water is 4.18 joules per gram degree Celsius. But you do need to know where to look in order to get that information. So table B, that's where you're going to get the specific heat of water. With that, we have enough information to solve the problem. So then we're simply plugging things in. Q equals 60 grams times 4.18 joules per gram degree Celsius times 20 degrees Celsius. And I wrote it this way for a reason, because I want you to have a look at the units. if you sort of consider that all of these are essentially a fraction and you're multiplying all the top numbers together, which is true, you are, then grams actually cancels out. The grams in the mass cancels out with the grams in the specific heat value. And then degrees Celsius, same thing, it cancels out, which means that the unit that you're left with is joules, right there. And so that's why when you solve for Q and Q equals MC delta T, the unit is going to be in joules. You've canceled the grams and you've canceled the degrees Celsius. Is this something I need you to explain to me on a test? Not really, but I do need you to know that Q is always going to be in joules, not kilojoules, when you're solving Q equals MC delta T. So then it's just multiplying these three numbers together, 60 times 4.18 times 20. When we do that, I get 5,016 joules. If I wanted to turn this into kilojoules, which question might be asking you to do that, remember there are 1,000 joules in 1 kilojoule. So I could do, using a T-chart, 5,016 joules, 1,000 joules on the bottom, 1 kilojoule on the top. That would be 5.016 kilojoules. Second problem, the temperature of a 95.4 gram piece of copper increases from 25 to 48 degrees Celsius. When the copper absorbs 489 joules of heat, what is the specific heat of copper? You can't simply tell me that it's 4.18 because that's the specific heat of water. We're no longer dealing with the same substance. Different substances have different specific heats. So we're going to have to calculate the specific heat. So again, we have Q equals MC delta T. Pulling apart the problem, what information do we know? We know the mass. We know the mass of this sample, 95.4 grams. The temperature increases from 25 degrees Celsius to 48 degrees Celsius. So we have delta T information. Remember, it's T final minus T initial. So we look at the temperature that it ended at. It went from 25 to 48. So that means that it ended at 48 and it started at 25. So we're going to do 48 minus 25. We get a delta T value of 23 degrees Celsius. When the copper absorbs 489 joules of heat. Remember, joules. That is not temperature. That's Q. We know the Q value. Reading this problem a little bit more, what is the specific heat of the copper? That's what we don't know. That's capital C. So capital C is specific heat. It's a constant like freezing point, boiling point, or density, and Q is just a certain value of heat that happened to occur in this one reaction. So we're simply going to plug everything in, and then we can solve for the specific heat of copper. So 489 joules of heat were exchanged. That was the Q value. The mass of the copper was 95.4 grams. Specific heat is what we're looking for. Delta T, temperature changed by 23 degrees Celsius. You want to be careful when you're multiplying and dividing here. Make sure you do this stepwise. Try to write down some intermediate numbers. Don't necessarily try to do this all at once. When you solve this, you should get a C value. The little Cu means copper, so I'm just indicating that we're looking for the specific heat of copper rather than the water. You get a value of 0.223. That should be what you get. Now, in terms of units, because we always know that you need units, the units for specific heat are kind of involved. They're a combination of 3 units because it's defined as the amount of heat, joules, required to raise the temperature of 1 gram by 1 degree Celsius, So it's joules per gram degree Celsius. If you have trouble remembering that, I will now remind you that the specific heat of water is listed with its units in table B of your reference table. So there's no excuse ever to not tell me the correct unit for specific heat if it's on your reference table, and you just need to remember to write down that weird looking thing that's right in front of you. So that's Q equals MC delta T, one of our 3 heat equations. The next up, the next heat equation for measuring heat flow, that's why I call it a heat equation, has to do with something called heat of fusion. Now, fusion means many different things in chemistry. In this context, it does not mean nuclear fusion, like the whiz-bang and lots of heat and energy, and we no longer have cities because we dropped a nuclear bomb on it. That's not the type of fusion that I'm referencing here. In this case, fusion means melting. It's much less exciting. It's a solid melting into a liquid, ice melting. That is called fusion in this context. And when that happens, when a solid melts, the solid and the liquid are both present at the exact same time. If you have ice melting in your cup, you don't just have ice and you don't just have liquid water, you have both of them. They are both there together. When a solid melts, both phases are present at the same time, right? The liquid phase and the solid phase. We say when they're present together at the same time, we say that they're in equilibrium with one another. So that phrase just means that both of them are there. Now, heat of fusion basically is saying what's the heat that's required to do that? How much heat is required to melt this solid? That's all heat of fusion means. And we use the capital H here. It doesn't stand for heat. That would make way too much sense. It actually stands for enthalpy. Remember that enthalpy from before basically just essentially means heat. They're all related to one another. And the little f next to this, HF right here, right, that's one thing, and it just means heat of fusion. So that's what the little f means. And it's the heat absorbed by 1 gram of a solid as it melts to a liquid. Now, absorbed, that's bolded and underlined because that means that this is an endothermic process. You want a solid to melt, you want a solid to turn into a liquid, you have to add energy to it. The solid doesn't have a lot of energy by definition. A liquid has more energy than a solid always. You want a solid to turn into a liquid, you have to give it energy. That's endothermic. This is an endothermic process. And if we have a look at table B, heat of fusion, that is a constant value for different substances. And the heat of fusion of water is listed on table B. So table B, those physical constants for water. Heat of fusion is the very first one there. 334 joules per gram. That means that if you have 1 gram of ice, it takes 334 joules to melt it. That's what this specific constant is saying. How much energy is needed to melt a solid? And going back to reference table T, the formula for calculating energy required to melt something, it's not just this going to be this 334, because that's 334 joules per 1 gram. Well, what if you don't have 1 gram? What if you have like 10 grams or 15 grams or 0.2 grams? Then how much energy is needed then? The formula is Q equals MHF. There are there's overall 3 components of this. There's Q, that's heat. There's M, that's mass, and then there's HF, that's heat of fusion. And that's a constant. The other 2 can change. You can change mass, you can change total heat exchanged, but you can't change HF. It's always going to be the same thing for a substance. For water, it's always 334. The opposite of fusion, if we sort of think about that, well, fusion means melting. So it's like saying, what's the opposite of melting? And hopefully you get that the opposite of melting is freezing, right? That's the opposite of melting. The opposite of melting is freezing. And so we call the opposite of heat of fusion heat of solidification. The heat lost, notice I have changed it, the heat lost, meaning we've switched to an exothermic process, when a liquid solidifies, when a liquid freezes. But the crucial thing about this is that we can actually use the exact same chemical formula for freezing as we can melting. We can use Q equals MHF for if we happen to have a liquid that is freezing, because they both involve the same phases. Fusion, which is melting, is a solid going to a liquid. Freezing is a liquid going to a solid. It's the same phase change, just different directions. Is your solid going to a liquid, or is a liquid going to the solid? The only thing that's actually changed is whether or not it's exothermic or endothermic. But the energy exchange, the amount of heat that would have to either go into or out of the system, is the same. The question is one of direction, not of magnitude. So practice problem with Q equals MHF. What is the heat absorbed by a 25.0 gram ice cube melting at 0 degrees Celsius? This is talking about melting, which means that we want to use Q equals MHF because, right, HF, fusion, that means melting. So pulling apart the problem, what information have they given us? Well, they've given us mass, we know that, 25.0 grams. They gave us this, 0 degrees Celsius. You have to think about what that is. Is that heat? No, it's not. That's temperature. So I'm going to label that as T. And then what are they asking for? What is the heat? That's Q, right? Remember, heat is Q. So that's what we're looking for. Okay, now looking at this formula. What have they given us versus what are they looking for? We know that we're looking for the value for Q. We know that they gave us mass. They gave us temperature, but they didn't give us HF. So then there's kind of a little bit of a quandary. What's going on here? And this is what I have to say about this type of problem. Where is T in this formula? Where do you see a capital T anywhere in this formula? That's right! There isn't one! There is no capital T! This piece of information is totally irrelevant to this problem. The only thing that 0 degrees Celsius is doing is telling you that, oh, okay, this is water. Water melts at 0 degrees Celsius. I know that. I know that we are, in fact, at the temperature under which this water undergoes a phase change. There is no temperature in this formula. Do not be tempted to plug that 0 in. You don't use it. You don't need it. It's irrelevant. It's there to try to get you to mess up. Don't fall for that trick. We have heat, mass, and heat of fusion, and that's all we need. We do need heat of fusion. We absolutely need heat of fusion to answer this question, which means we have to get that value from somewhere. Table B. Look it up. What is the heat of fusion of water? 334 joules per gram. Now we have absolutely everything we need. We're looking for Q. The mass of the water is 25 grams. The heat of fusion of water, is 334 joules per gram. 1 gram requires 334 joules, so 25 grams will require 25 times 334 joules in order to melt it. The grams actually cancel out. They're on top and they're on bottom, which means that the unit that we're going to be left with for Q is going to be joules. 25 times 334, that's 8,350 joules required to melt that 25-gram ice cube, or if we turn this into kilojoules, 8.35 kilojoules. 0 degrees Celsius temperature is not a part of this equation. You are not plugging it in. Heat and temperature are not the same thing. Heat is Q, temperature is T. T is not part of the formula. Don't try to use it. And then heat of vaporization, same kind of thing. So fusion is about melting and or solidifying, because we can use Q equals MHF for freezing as well. So we're going to talk about vaporization for that other sort of set of phase changes. Vaporization is a liquid turning into a gas. That's boiling, sort of using the colloquial term. And when that happens, when a liquid turns into a gas, this is very similar to the stuff as before, the liquid and the gas are present at the same time. We say that they are in equilibrium with one another. When you have water on the stove that's boiling, it didn't just suddenly all disappear and turn into gas. You have both gaseous water and liquid water present together at the exact same time. Now, in order to boil something, you can talk about its heat of vaporization, HV. So this is like HF, only now it's, HV because it's heat of vaporization. And it's the heat absorbed by 1 gram of a liquid as it vaporizes into a gas. And this is an endothermic process, and it's a constant value. It's always going to be the same for any given substance. Water, table B, heat of vaporization of water. Oh, look, table B, list of physical constants for water. We're going to be using those. 2,260 joules per gram. So you want to boil water. Guess what? It takes more energy than it takes to melt the water because you're completely separating the water molecules from one another now. You're breaking all of the IMFs rather than just a few of them, which takes more energy. So if you had something other than water, it would not be 2,260. It would be a different heat of vaporization. It would be a different constant. If we use this, if we go back to table T, our third heat equation that's listed in table T is Q equals mHV. Again, there are three components of this. There's Q, that's heat. There's M, that's mass. And then there's HV. So HV is one thing. It's the heat of vaporization. And that's a constant value. It will not change. So this is a constant for a substance. And the opposite of vaporization, the opposite of a liquid turning into a gas is a gas turning into a liquid. That's the opposite of that process. If you think about what that's called condensation. When a gas turns into a liquid, right? Condensation on our bathroom mirror in the morning. The water vapor that was in the air condensed on the mirror because the mirror was cooler, so it was able to change phases of matter. And this is the heat lost when a gas condenses, so this is an exothermic process. So vaporization, boiling, that's endothermic, that requires heat. Condensing, that is exothermic, that actually releases heat. I'm going to talk a little bit more about these phase changes later. But the key, very similar to sort of the last one, you can use Q equals mHV for condensation as well as vaporization. The difference is that with condensation, that's losing a certain amount of heat. With vaporization, that's gaining it. But the phases involved, gas to liquid versus liquid to gas, they're the same phases. So that's why we're allowed to use Q equals mHV for both of these phase changes. They both involve the same two phases of matter. So sample question with this. What is the heat absorbed by 42.5 grams of liquid water as it vaporizes at 100 degrees Celsius? So we have this word vaporizes, which is our key that we want to use this formula, Q equals mHV, because we know that we're talking about something turning from a liquid into a gas. What information do we know? We know the mass. We know that the mass of this sample is 42.5 grams. Backing up a little to the beginning of the question, it says, what is the heat? Remember, heat, that's Q. Q and temperature are not the same thing. Heat and temperature are two different things. So we are looking for Q, and hopefully you can anticipate Mrs. Julian's slight little freak out, because reading this right here, there is no temperature in this formula. There is no T anywhere in this equation. You want to calculate heat of a phase change? Who cares the temperature that it's at? Unimportant. Do not care. Irrelevant. Not a part of the question. Why did they give it to you then? To confirm that, yeah, this is water, and water vaporizes at 100 degrees Celsius. Yes, we are at the correct temperature for this water to undergo this phase change. Is it a part of the formula? No! Do not use it. Temperature is irrelevant. What do we need, though, if we want to get Q? We need HV. Where are we going to get that? Hopefully by now, you're starting to realize Table B. Table B lists some of these heat constants for water. So that's 2,260 joules per gram. So all we need to do is plug in. So let's see, we've got 42.5 grams times the 2,260 joules per gram. Right, 1 gram needs 2,260 joules to boil, but we don't have 1 gram. We've got 42.5 grams, so it's going to take 42.5 times as much. So then we're just multiplying those numbers together. When we do that, with a little bit of rounding, I get Q of about 96,000 joules, or approximately 96 kilojoules. Now, with using these three heat equations, using them is actually not all that hard. But the critical thing is that you have to know when to use which one. So we have three of them: Q equals MC delta T, Q equals MHF, Q equals MHV. And the problem isn't going to tell you which heat equation to use. This is probably the most involved part of the three heat equations, knowing when to use which one. So the first one, use Q equals MC delta T when. What are the key words in the problem that you would want to really latch onto? The distinction between them, the thing that sets Q equals MC delta T apart from the other two, is really the inclusion of temperature. Temperature change matters with Q equals MC delta T. Notice that T is not a part of the other two heat equations. It's just not there. So if you are changing temperature, if you are heating something up or you are cooling it down, if the temperature is changing, that's when we use Q equals MC delta T. Do not rely on the C component, because that's given in Table B, and you'll be expected to know that it's there and get it of your own accord. So you can't simply rely on them giving you a specific heat. Now, they might ask for specific heat, which would be a great clue to use this one, but you'll always have information about change in temperature, or they'll be asking you what the change in temperature is, or how much did the temperature go up by, or hey, these are the two temperatures that it started at and then the one that it ended at. Q equals MHF. How are you going to know to use Q equals MHF? Again, you want to look at what makes this equation different from the other two. And the thing that makes it different from the other two is the HF bit. So what does that F stand for? That F stands for fusion. What is fusion in this context? Melting. If the problem describes something melting or something freezing, because remember you can use this for freezing as well, or uses the word solidification, which is just a fancy word for freezing, or uses the word crystallization, which is just a fancy word for freezing, then we want to use Q equals MHF. Mass times heat of fusion gives the amount of heat required to melt something. And then the last one, Q equals MHV. When are we going to use Q equals MHV? Again, you're looking for what makes this formula different from the other two. And the thing that sets it apart is the HV. That's unique to this formula. So HV, what does HV stand for? Heat of vaporization. What does vaporization mean? Vaporization means boiling. Vaporization means a liquid turning into a gas. We can also use it if something is undergoing condensation. So you want to look for those key words. If the problem talks about boiling or vaporizing or condensing, then you're going to use Q equals MHV. Remember that Table B contains these constants for water, but if you don't have water, then you cannot use the stuff in Table B. The stuff in Table B is just for water only. Now, water is going to be your substance in most of the cases, but don't rely on it, right? It might be something other than water, like that copper example that we did for specific heat. You can't use water's values. All right, so that's that last bit. If the substance is water, use Table B. If not, you need to look for information in the problem itself, and then that'll help you answer the question. So for the rest of the time today, I'd like you to get started on the homework. And the first thing that I recommend doing on the homework is actually sort of going through and figuring out which formula you need to use for which question. So read through the problem, and before you do any math, just write down, are you using Q equals MC delta T, Q equals MHF, or Q equals MHV? Do that for all the questions first, then you can go back and start doing the math now that you know which formula you need to use. Remember, look for these key terms to identify which heat equation will be used for which problem.